All right, then let's start. Welcome to my talk about knapsack with small items in near quadratic time. So we all know the knapsack problem. Given n items, each item has a profit pi and a weight wi. We also have a weight budget, which I denote by big W, and we want to select some subset of the items such that the total weight is at most the weight budget and the total profit is maximized. This problem is also sometimes called 0-1 knapsack. There are other versions of the problem, for example, the bounded knapsack problem, where you additionally have multiplicities. This can be written in this form here, that now the profit vector, the profits are a vector, and PTX, this inner product, is just the total profit of solution X. We want the total weight to be at most the weight budget. And now X can be any integer vector, such that X lies between 0 and U, which means that Xi lies between 0 and Ui. Or in other words, we are given a multiplicity ui for every item I. We can choose item I up to ui times. Both of them are NP-complete and fundamental problems. We are probably more used to the former one. The second one is maybe more natural if you work in mathematical optimization. What I will tell you about will hold for both versions of this problem. I will mostly focus on the 0-1 knapsack. All right, so what do we know about it? Most certainly, we all know that one can solve it with dynamic programming in pseudo-polynomial time n times w, number of items times weight budget. There have been a couple of lower bounds that show that this running time is likely close to optimal. So for example, if you want sublinear dependence on the weight budget, then you have to pay an exponential factor in n. That's roughly what this lower bound is saying. And it's also known that one cannot solve it in n plus w to the 1.99. So kind of this quadratic dependence on n and w is necessary. And there's some other hypothesis. So kind of we understand that this algorithm, that it's close to best possible. So once we are finished with one parameterization of the problem, it's natural to look at other parameters. For example, at the maximum weight of any item, little w max. That's another parameter. If we could replace big W by W max, it would be good in general, right? Because it's a smaller parameter, so it just makes sense to study it. And then, now we fix the parameterization to n, the number of items, and W max. We can again ask, what is the optimal running time of the problem in terms of these parameters? Let's first ask, is it in polynomial time in these two parameters? If it is, what is the optimal exponent? What is the optimal smallest c, let's say, such that it is in time n plus W max to the c? For 0-1 knapsack, it's quite easy to see that it is in polynomial time in n and W max. Because if the weight budget is more than the largest weight times the number of items, we can just pick all the items and we have a trivial instance, so we don't have to do anything. So really we can assume that the weight budget is at most n times W max, and then this classic Bellman DP runs in time n times W, which is now n squared, bounded by n squared W max. So certainly we can do it in polynomial time in these two parameters. The lower bound that I told you before of n plus w to the 1.99, it actually transfers to this setting simply because W max is a smaller parameter than W. So if you could solve it in subquadratic time in n plus W max, you could also solve it in subquadratic time in n plus W, which was ruled out by the previous slide. So the best optimal exponent, combined exponent C, lies somewhere between 3 and 2. That's what we know from this slide. For bounded knapsack, situation is actually more complicated because you have these multiplicities. So the optimal solution could consist of many items. The number of items in the optimal solution does not need to be bounded by polynomial and n and W max, because the multiplicities could be huge. And that's why the naive DP does not solve it in this running time. It can still be solved in this time, but it's not trivial. And the same lower bound also applies. Okay. So starting from Bellman's algorithm, Tamir was the first to show that also bounded knapsack can be solved in polynomial time in these two parameters. And then there was a long chain of work of faster and faster algorithms in terms of these two parameters. Some only work for 0, 1 knapsack, some work for the more general bounded knapsack. I marked the ones that actually improve the combined exponent, right? And for bounded knapsack, this used to be 5, and then it was reduced to 4, and then to 3. Right. So what is the exponent of n plus the exponent of W max? And the lower bound is, it cannot be less than 2. Right, so this was the state of the art until about a year ago. And then there was an intense month of first Sijin putting a paper on archive with exponent 2.5. And independently, Chen et al., they reduced it further to 2.4. And this was presented at SODA. And then I improved it further to Quadratic. And independently, Sijin also improved it to Quadratic. So that's why we are sharing this talk slot at STOC. All right, so now at least this quest came to an end. It can actually be solved in quadratic time or with combined exponent 2, and cannot be solved with combined exponent less than 2. So this is a near optimal algorithm. Of course, it doesn't mean that there are no further open problems, but let's come to that later. All right, so in the rest of my time, I want to talk to you about how to get quadratic time. There will be 2 ingredients to get this algorithm. One is relatively classic, namely max plus convolution on concave sequences. And then the other one is a more recent line of work on proximity bounds. Throughout the talk, I will only consider the 0-1 knapsack problem. I will also assume that no 2 items have the same profit to weight ratio and that no 2 items have the same weight. The first 2 assumptions are really without loss of generality. So there are reductions, not simple reductions, but there are reductions that ensure the first 2 assumptions. The last one is really not without loss of generality. So one has to do has to do more work and also put in more ideas to cover the case where items can have the same weight, but I will not talk about it in this presentation. Good. Let's start easy with the profit function of the standard 0-1 knapsack problem. If this is my instance, then I want to look at the profit function, which gives me for every possible weight bound, what is the optimal profit if that is my weight bound. So this is this function here. If my weight bound is 0, I cannot get any profit. If my weight bound is 2, then I can get a profit of 5, for example, by picking the first item. My weight bound is 5, I can get a profit of 8 by picking these 2 items. So for any possible weight bound, what is the optimal profit? This is what is called the profit function of a knapsack instance. All right. Profit function allows us to write how it works to combine subproblems of knapsack. If I already have the profit function for some subset of items I, and I have the profit function for another subset of items j, I can combine these profit functions to the profit function of the union of I and j. And this combination operation is just this here. Namely, if I have a weight budget k for the overall problem, then I somehow have to split this weight budget into a budget I for I and a budget j for j. And these 2 budgets should sum up to k. I cannot pick more than k. Right, and I maximize over this because I want to maximize the profit. Okay, so this is how I can combine subproblems. And this operation here also has a name. And this is called the max plus convolution of these 2 functions, fi and fj. Right, because of this max and this plus, and this is the max plus convolution. So what is known about max plus convolution? In general, this is a difficult problem in the sense that the naive algorithm solves this in quadratic time, so w squared if the sequence length is w, and it's conjectured to actually require essentially quadratic time. But there are many special cases of the problem that can be solved faster. And one important special case is when one of the sequences is concave. And that can actually be solved in linear time, which dates back to 2004. Keller and Freshy, they solved it in w log w actually. And then later Axiotis and Samos, they observed that the SMOG algorithm can be applied and solve it in linear time. So this special case can be solved fast, which immediately gives rise to an interesting algorithm for Knapsack. Namely, what can we do? We take all the items, we split them into weight classes. So inside groups of weights, so inside one group, all items have the same weight. If all items have the same weight, then Knapsack is actually super easy because then the greedy algorithm works. You simply want to pick the item with largest profit first, and then the one with next largest profit, and so on. It turns out that the profit function then also is a concave function. You get this diminishing returns property. So inside every group, the problem can be easily solved in linear time by a greedy algorithm. And the resulting profit function inside every group is concave. So all that remains is to combine all the groups. So let's start with the profit function for the first group, combine it with the second group. Well, this is a concave function, so we can apply this special case and do it in linear time. And we have the combined profit function of the first two group, take the third group, combine it. This is a concave function. So each of these steps runs in W time. How many steps do we have? Well, exactly the number of distinct weights in the instance. So the running time will be number of distinct weights times the weight budget W. All right, that's the first ingredient. And the second line of ingredients is proximity bounds. That's here we start from the maximal prefix solution. So we're given some instance of 0, 1 Knapsack. We sort the items by decreasing profit to weight ratio. So the left items in the figure here are the ones that have that are very good. They have a very large profit to weight ratio, and the right ones are relatively bad. And what we just look at is the largest prefix of these items that we can still fit into our Knapsack. This is a very naive greedy solution, right? It's not even really the greedy solution, because the greedy solution would try out some other items whether you could still add it. For the maximal prefix, you really stop once the next item doesn't fit anymore. So naive greedy somehow. Right? And whoa. And we want to compare this to the any optimal solution, X star. So let's fix an optimal solution. Intuitively, it should look kind of similar to this maximum prefix solution, right? The maximum prefix chooses items with a large profit to weight ratio. The optimal solution better also chooses items with large profit to weight ratio. So intuitively, they should not differ by a lot. And this one can actually prove. Eisenbrandt and Weismantel were the first to pioneer this proximity bound, where they showed that the G and X star, they differ by at most 2 W max many items, which also implies that they differ by total weight at most roughly W max squared. All right. This is useful for Knapsack. Let me show you that it's useful for Knapsack. Pollack et al., they got this algorithm in time W max cubed, where they use dynamic programming, but not to search for X star, but to search for the difference of G and X star. Which item do I need to add to G? Which items do I want to remove from G to get to X star? And so it's a bit more general dynamic programming, but it still works to search for the difference of these two. And then with the length of the DP that is no longer related to the weight budget, but only to the total weight of the difference. And we have a bound on this weight due to this proximity bound, so that's good. And the rest of the algorithm follows the previous algorithm that we've seen. So we partition items according to weight, and we combine weight classes by max plus convolution, where one side is concave. And the running time that we get is, well, we have number of distinct weights, many weight classes, weight groups. Inside every group, we have to fill a DP table whose bound is dependent on the total weight difference of G and X star. We have bounds on these two, right? The weight difference is at most W max squared. The number of distinct weights, well, certainly is at most W max. We get W max cubed. That's their algorithm. That's Pollack et al. Algorithm. All right, so that was the state of the art a year ago. And then people ask the question of whether this term here, this product of these two, can be more directly bounded, right? Because we're losing quite a lot in bounding them independently. Can we somehow get a proximity bound that really looks at these two terms in combination, the product of these two terms? And at best, we can hope to reduce this bound to Wmax squared. And indeed, Chen et al., they came up with an improved bound. They showed that one can efficiently find a partitioning of the items into k parts, such that within each part, the number of distinct weights times the weight difference of greedy and optimal solution. This is small. It's at most Wmax to the 2.4. And in their partitioning, they used some constant number of parts, 6, I think. And then in the improvement that I came up with, I reduced the exponent further to just Wmax squared, while increasing the number of parts to polylog, log squared. All right. And now, I mean, should be kind of intuitive that once we have a bound on this kind of product, then basically on each part here, we can run this type of algorithm to improve the running time from cubed to squared. One has to adapt the algorithm a little bit, of course, to incorporate that we have this partitioning and that we have to somehow combine the different parts of this partitioning. But there's only a polylog number of parts, so we can do that efficiently. I'm not going to talk about this. Good. So now I explained to you naturally how this line of algorithms developed, why this proximity bound here is useful in that it gives rise to a faster algorithm. Now all that is left is to actually prove this proximity bound. So let me give you a little bit of an overview of how to prove this type of proximity bound. And this builds on work in additive combinatorics. There is this line of work that, or maybe even a research area, where one of the central results is this one here, that if you have a set of integers bounded by some number, in this case, I want this number to be Wmax, and the set of integers is kind of big, it's more than square root Wmax, and by this more and more I'm hiding constant factors, I'm also hiding logarithmic factors. So if it's much more than square root size, then if you look at the set of all subset sums of this set A, this contains a long arithmetic progression. This is an existential result in additive combinatorics, which is a subfield of mathematics. So it's not immediately clear why this is interesting or what applications it has, naturally. There's a long line of work on this, like where these bounds were improved and it was generalized and so on. There's also a long line of work that tries to use this result and similar results to solve subset sum and subset sum-like problems, starting already in the 90s and continuing till today. And it kind of makes sense to use this type of result for subset sum because it's talking about subset sums. It's much less clear how to apply this kind of thing for Knapsack because we're not only talking about sets of numbers, we have weights and profits. Anyway, so if you look into the literature of this type of result and relate it, then one can distill the following result from that. So this theorem can more or less be found in this literature, or at least it can be easily proven by combining some lemmas on this literature. So this is basically what follows from additive combinatorics, namely that if you have two sets of integers bounded by Wmax, and the set A has large size, and the set B has large sum, whatever large exactly means, then they have two non-empty subsets. So A has a non-empty subset, B has a non-empty subset, and they both have the same sum. This is somehow useful to end up at arithmetic progressions. I'm not going to go into detail of this. What I want to show you is how this can be useful for Knapsack. Right, and if you want to handle the case of Knapsack where items can have equal weight, multiple items can have equal weight, then we actually need a generalization of this to multisets. Let me also not go into this. Good. So let's get back to this maximal prefix solution and optimal solution. I want to prove this in a proximity bound. The proof has a couple of cases. I will only really look at one of the cases. So let me assume that n is big enough, because there will be some other case where n is small and it will be handled in some way. And let me not get into it. Let me also assume that greedy selects at least half of the items. Again, there will be a more or less symmetric case where this is not the case. And then let's split the items selected by greedy at the median, so into the more profitable half and the less profitable half, I and j. And now let's look at the items in j selected by the optimal solution. And let's look at the items in, and again, another case assumption is that the optimal solution selects at least half of the items in here. Let's also look at the items in I that are not selected by the optimal solution, so the empty spaces here. Okay, so those are sets of items. In the end, I want to apply this theorem here to sets of numbers. So let's also look at just the weights of these items and the weights of these items. So this set A and B, this is what I want to apply this theorem on. And I want to argue that the theorem cannot be applicable to A and B. Because if it would be applicable, then we would find two subsets of these items that have the same sum. So that means when I go back to B hat and A hat, I would find two sets of items with the same weight, same total weight. They have the same total weight, then I can exchange them. I can add one to X, remove the other from X. I don't change the total weight, so it's still a feasible solution. And what I add is from the left part, what I remove is from the right part. So I get those items here have higher profit to weight ratio, those have smaller profit to weight ratio. So I'm really increasing the profit. So that would contradict X star being an optimal solution. So it cannot be that this theorem is applicable, because this would contradict optimality of X star. So let's look into the assumptions of this theorem here. I claim that the first assumption is actually satisfied, really by the case assumption. So the size of A is equal to the size of A hat, which is at least half of the size of J, which is half of the size of G, which is at least half of N. So if you follow all these case assumptions, the size of A is omega N, and we assume that N is at least root W max. So this whole thing is at least is much more than root W max, which means the first assumption here will always be satisfied. So to conclude, the second assumption cannot be satisfied. Whatever we do, the second assumption must be wrong. So the total sum of B must be at most roughly W max squared over A. The way that we chose A, it has roughly the same size as I. And now what is the sum of B? B was the weights in B hat. So this is the total weight of the items in B hat. And the items in B hat are those not selected by X star, but selected by G. So the sum of B is exactly the weight difference of the greedy solution and the optimal solution constrained on the set I. There are two more simple things here. The number of distinct weights in I is certainly at most the size of I. And the size of I is linear in N, again, by all these case assumptions. That's all that we want to need, that we need here, that we can find the set I that satisfies these things here. Because then we basically get the proximity bound, right? This here is the proximity bound that we wanted to end up with. The number of distinct weights inside I is at most I. The total weight difference inside I is at most W squared divided by I. So the I's cancel and we end up at W squared. So what we did now is we found one part of this partitioning here. And what we can do, and this has linear size, theta of n, so we can remove these elements, recurse on the rest. We will end up with a logarithmic number of parts. Once you generalize this to include multiplicities, so multiple items of the same weight, one can generalize this and end up at log squared n parts. But anyways. All right, that was the proof overview. that shows roughly how one can end up at n plus w max squared. I think I will stop here for the recording.